Hi everyone, welcome to Module 5 for Kinesiology 7103, which is taught in the Department of Health Kinesiology and Recreation here at the University of Utah. In today's module, we're going to be talking about statistical inferences about parameters in our general linear model. So at the moment, we're building a relatively simple model in which we're going to have a slope and an intercept for a continuous variable, and we're going to try to decide how we can make statistical inferences about what's happening in our sample and apply that information back to what might be happening in the population. So in previous lectures, we've shown you how to calculate the estimates for our two linear parameters, being the slope and the intercept. We also showed how to interpret these parameters, especially as the 0 point on x was changed or the scale on x was changed, right? And changing the 0 point, right, sort of what an x of 0 means, had an effect on the intercept. Changing the scale of x had an effect on the slope, because the intercept is the predicted value of y when x is 0, and the slope is the change in y for a 1 unit change in x. So if we change what the 0 point means, right, we're changing the interpretation of the intercept. And if we're changing the scale of x, then we're changing what a 1 unit change in x actually means. So now we're going to address how to make statistical inferences about these parameters, which is to say, given what we observe in the sample, what can we say about what might be happening in the population? So we started with this model comparison idea in which we were looking at household internet access in the 50 different US states as a function of their college graduation rates, and we wanted to see if these things were related. So we were going to compare a compact model, right, model C, in which we just estimated the mean household internet access for everyone, to a model in which we made a conditional prediction, model A, in which we said we're going to estimate your internet access rates as a function of some intercept plus a slope times the college graduation rates, and we want to see if this statistically improves the fit of our model. And visually, right, we're asking, is this sloped line better than estimating the mean for everyone, or estimating a flat line running through the center of our distribution? Intuitively, it looks like it's going to be, right? But we'd like to actually have a bit more clarity, something maybe a little bit more objective than our intuitions. So one method for formalizing this is to compare the squared errors in those different distributions. In order to compare those squared errors, right, we need estimates for the slope and the intercept. So in the previous videos, we walked through how to calculate those, right? So here's our formula for the calculation of the slope. Here's our formula for the calculation of the intercept. Note that the slope has to be calculated first because it's included for our formula in the calculation of the intercept. And then we walked through how to do that using the raw data. We will get statistical programs to do this for us, by and large, in the future, right? But it's good to go through and by hand actually derive these calculations and calculate your model's predictions so that you really understand what the computer is doing as you move forward. So once we had those, right, once we had our slope and we had our intercept, we're actually able to make some statistical inferences about these different parameters. And to start with, we're going to make statistical inferences about the slope. Okay, so to see how much the inclusion of the slope, beta 1, improves our model, we need to calculate the proportional reduction in error for that model A to model C comparison that we set up at the beginning. Right? And the proportional reduction in error, as a reminder, is the sum of squared errors from our compact model, where we're just estimating the mean for everyone, minus the sum of squared errors for our augmented model, where we have a mean and an intercept, which are generating our predictions, divided again by the sum of squared errors for the compact model. And again, to break out those sums of squared errors, you can see, right, SSEC is just each person's score minus the mean squared, and then we add all those squared deviations together. SSEA is each person's score minus the model prediction squared, and then we add all of those squared deviations together. And if we wanted to see that represented in more detail, we could actually write out what those model predictions are, right? It would be the fitted value of our intercept plus the fitted value of our slope times x. When we add these together, right, that's the same as y hat, because those are our model predictions. It's x times the slope plus the intercept. And we're going to look at the discrepancy, right, or the error between that and our actual data. And again, once we add all of those squared deviates together, we'll have the sum of squared errors for both of our models, and that will allow us to start to make our model comparison. So you can see this as what we'll walk through in the lab, and this is what it would look like if you did it for these data in R. We're going to create the model predictions, which I've called y_c for the compact model. And you can see we're estimating the same value for everyone in the compact model because, again, we're just estimating the mean for everyone. which means then we're going to have E underscore C, right? So these are the errors under the compact model. These are the deviations away from the mean. We'll also get model predictions for the augmented model, Y underscore A, and you can see here under the augmented model, each state gets a unique prediction, okay? And the reason for that, of course, being is that each state has a unique value of X. So X is getting multiplied by the slope and added to the intercept to generate these predictions. And then we can subtract YA from the actual internet access to get the errors under the augmented model, which are shown here. Once we have those errors, we can square them and add them together to calculate our sums of squared error estimates. And in this case, it's 1,355 minus 480 divided by 1,355. And if you do that, we get a proportional reduction of error of approximately 0.65, let's say. Once we have that calculation of pre, then we can actually calculate the F statistic. And recall that F observed takes the form of the proportional reduction in error divided by the number of parameters in Model A minus the parameters in Model C. So this is essentially how much variation are we explaining per parameter divided by 1 minus the proportional reduction in error divided by the residual degrees of freedom. So we're saying, okay, how much variance did we explain per parameter versus how much error do we have left over per degree of freedom? So by standardizing those two, we can actually create a reasonable ratio. And in this case, the F observed value is 87.5. So this is a pretty big change. We explained a lot of variation in our data by the inclusion of this parameter in our model. But 87.5, right, is big. But how big is it? We actually need to calculate a probability of observing this F observed value given our null hypothesis. So we can compare this F observed to the null distribution for an F with 1 and 48 degrees of freedom. So what we've plotted here, right, is the F observed, or the density of the F distribution with 1 and 48 degrees of freedom from F values of 0 to 10. The actual critical value in this case is 4.0247. And again, the F critical value corresponds to our alpha value. So assuming we set a false positive rate of 0.05, we'd actually draw that critical line here. Now 95% of this density function is to the left, right? 95% of the area under the curve is to the left of 4.0247. Only 5% of that is to the right of 0.0247. So anything greater than this, we would expect to see, due to sampling variability alone, less than 5% of the time under the null distribution. And of course, our F observed value is quite a bit bigger than this, right? Our F observed value was 87.5, so it's going to be somewhere all the way over here off the screen. So this is definitely a statistically interesting value. It's much larger than we would expect under the null distribution, and therefore it is unlikely to have arisen by chance alone, assuming the null. So this seems like a statistically interesting effect, and there might be a relationship here between internet access rates in the various states and their college graduation rates. And if we actually wanted to calculate the p-value for this, we could use the probability of F function in R, right? Because we can compare F observed to F critical, and we know that the probability is less than 0.05, but what exactly is it? It turns out this is very, very small, right? So if for shorthand, I've kind of written this as just less than 0.001. So this is very unlikely to have arisen given the null distribution. We can compare this then to the linear modeling output that we get from R to show you the things that we've calculated by hand and how it corresponds to what we get out of R, and then some of the things that we haven't actually calculated yet. So the black and bolded text are the things that we get out of R that we've already shown you how to calculate by hand. The things that are bold and in red show you things that we get out of R that the book also walks us through, and we will spend a little bit of time on in lab. But I just want to take a second to talk about these and then talk about what else remains to be done. So thus far, we've shown how R is calculating the point estimate for both the intercept and the slope. We've shown how R is calculating the R squared, right, or the proportional reduction in error for this augmented model. And we've shown you how to calculate the F observed, or how R is calculating the F observed for this model as a whole, when we are testing, something where we include the slope against the model C, in which the slope is set to 0. Now, in the book, they talk about how we can make a corresponding t-test and the t and the f test, when we have 1 degree of freedom in the numerator, are transforms of each other. They're highly related, right? So these parameter tests, these single parameter tests, can also be achieved with a t-test, which is why R is giving us a t-test here. And we're going to walk through this calculation a little bit more in the lab. And R also gives us the adjusted or the unbiased R squared, right, which is just a transformation of the multiple R squared to account for having some variation always being explained by chance. So we haven't worked through that, but it's a relatively easy adjustment that they show you how to make in the book. One thing we haven't talked about yet, though, is that we need to understand how R is making a statistical inference about the intercept beta 0. Okay, so we can see that we're getting a p-value here for the slope of college, right, the effective college graduation rates. That corresponds actually to the p-value for the model, which makes sense because we're comparing a model A, where the slope is not equal to 0, to a model C, in which the slope is being set to 0. But it's not going to be intuitive. Well, what is R actually doing when it calculates this p-value for the intercept? And can we show what R is actually doing under the hood in order to generate that statistical inference? Well, recall that the point estimate for beta 0 is calculated after beta 1, right? So when we're fitting these things, we calculate b0 as the average y minus the slope times the average x. And this is because having a slope in our model changes the value of the intercept actually means. So it's always going to be the predicted y when x is 0. So when we're doing our statistical test for the slope, right, we have a parameter for the intercept in model C, but we don't have one for the slope. And we don't have one, but what's implicit in that is that we're actually saying this slope is equal to 0. We're saying in a model where beta 1 is fit from the data versus a model where we force beta 1 to be 0. So in this case, if beta 1 is 0 and we're not conditioning our prediction based on graduation rates, then we're going to estimate the mean for everyone, and that will be the best fitting slope in this distribution. Or sorry, the best fitting intercept for this distribution of data. And we can compare that then to a statistical test for the intercept, which is actually just doing the reverse. So when R is calculating that p-value for the intercept, what it's doing is comparing the same model A, right, a model in which we have both the intercept and the slope as parameters, to a model C in which we have a slope, but we force the intercept to be 0. So if we say, okay, there's a 0 intercept, but then there's a slope, how small is that sum of squared errors compared to the model A that we have here? And when you do that, right, you can calculate an SSEC and an SSEA the same way that we did before. You can then calculate a proportional reduction in error between those two models, and from that you can calculate an F observed given the same degrees of freedom. Right? So we're going to get an F with 1 in 48 degrees of freedom, which is equal to 315.24, which again corresponds to a very small p-value under the null distribution. So although R presents this result as a t-test, the results are equivalent. So R, gives us a t-test of 17.755, and so it tells us that p-value is very, very small. If you just square that, you get 315.24, right, which is the same F value that we got here, and generates the same p-value. So for the same degrees of freedom, a t of 17.755 gives you the same probability as an F test with 315.24, because again, these are asking equivalent questions. It's just one is modeling this with a t distribution, one is modeling this with an F distribution, but you arrive at the same answer. And again, in the lab, we'll talk about sort of doing these calculations with the t distribution for the individual parameters, whereas in the book, we mostly focus on doing it with the F distribution. So ultimately, then, what this is going to mean is that we conclude that our observed intercept of 47.91 is unlikely to have arisen under the null hypothesis, right, in which we assumed that beta 0 was equal to 0, right? So you can see in model C here, we assumed that beta 0 is equal to 0, contrasting that against a beta 0 that we allowed to be free to vary. And when we actually fit those models, model A is statistically better than model C, which means that the intercept is actually unlikely to be 0 in this situation. So again, just to kind of break out this linear model output from R, right, we haven't shown how to do the F test or the t-test as an equivalent to the F test, although we talked about this in the book and we're going to talk about this in lab, but we have shown you how to get these p-values, because you can do an f-test for both the intercept and the slope, and that's what we've walked through here. Right? We are asking effectively if each individual parameter is statistically different from 0, but what we actually have to ask those questions are two different model comparisons. The model A is the same in both cases. We have a model A with 2 parameters here, and we have a model A with 2 parameters here. For the test of the intercept, our model C forces the intercept to be 0. For the statistical test of the slope, our model C forces the slope to be 0. But in both cases, the same logic applies. We're going to calculate the proportional reduction in error for this model comparison and turn it into an F observed value, and then we're going to look at that F observed relative to the null distribution. For the slope, we're going to calculate the proportional reduction in error for this model comparison. We're going to turn that into an F observed value, and then we're going to look at that F observed value relative to the null distribution. And that will allow us to answer the question, is the intercept statistically different from 0, and is the slope statistically different from 0? And if they are different enough, right, if those p-values are lower than what we've set our false positive rate to be, then we would say that, yes, that's a statistically interesting effect, and we would conclude that there is likely some sort of relationship between those factors, right, in the case of the slope. Right? There's a non-zero relationship between college graduation rates and internet access rates. And we would also say that the intercept is statistically different from 0, but that's a little bit harder to interpret and not necessarily very theoretically meaningful in this situation, because this is just telling us that the predicted value for a state with a 0 college graduation rate, we still expect them to have about 48% internet access. So statistical questions about the intercept aren't always going to be the most interesting or relevant to scientific theories, although they certainly can be. But we're really going to focus on these statistical tests of the slope because those are going to tell us about relationships between the variables in our model.